And let's see, so it's counterclockwise. Let's see, it's counterclockwise. As the particle travels counterclockwise around a circle. Where'd it go? With center 1, 3. And radius 1. And it completes a revolution in, what did I say, 3 seconds? Yeah, okay. So that means, so it's a circle. I'm going to travel counterclockwise. So I'm going to go this way around the circle. It's centered at 1, 3. I'm going to go counterclockwise around this circle, and it's going to take me 3 seconds to get around the whole thing. So at t equals 0, I should be here, and at t equal to 3, I should be back here. So this is really about, this is 2 levels to this. First off, the rectangular to polar. You start at polar. You got to figure out how to get the center to be in the correct place. Right? Pretend like my picture is actually a circle. And then you have to figure out, the big thing is figure out how to make it complete in 3 seconds. Right? So let me ask you guys, can you give me just the equation of a circle centered at the origin?
X squared plus y squared equals 1.
Yeah, x squared plus y squared equals 1. What is x squared plus y squared in? Oh, wait a minute. Okay. Oh, well, sorry, I'm going to get confused. We're about to do polar coordinates, which is sort of related to this, but it's not the same thing. So, remember what we did for a circle? We let x equal to, who remembers? Cosine theta. And y equal to sine theta, right? That would create, so if I let, and let's make t's here instead of theta, is that cool? And that would make the circle, right? In fact, if you check it out, is it going counterclockwise? When t is 0, what's x? When t is 0, x is 1, and y is 0, right? When t is pi over 2, x is 0, y is 1. So sure enough, it's going counterclockwise, correct? Now it's got a few things going wrong for it. How many seconds, if we look at t as seconds, how many seconds does it take for it to go all the way around the circle? 2 pi seconds. Does anyone remember what that's also referred to as in trigonometry? If it takes it 2 pi seconds to get through a whole wave's length, a whole cycle. Period. So the period currently is of course 2 pi, which makes sense because that's the period for both of these guys. Right? We need the period to be what? So there's a few problems with this. Number 1, the center's not correct. You with me? I really want you to understand. But is it going counterclockwise? Yes. As we started to throw in values of t, it is going counterclockwise. That's the only thing we got going for us. This does not have the right center, and it doesn't take the appropriate amount of time to complete one revolution. Do you guys remember how to control the period? For example, do you guys remember what the period would be for this? So this period is 2 pi. What's the period for this?
2 pi over k.
2 pi over k.
Okay.
It smushes it, or lengthens it, depending on what the value of k is. So if k is bigger than 1, it'll smoosh it. If k is less than 1, it'll stretch it. Do you guys vaguely remember this from trig? If you're out there like I never took trig, don't. I'm sorry, you shouldn't be here, but that's all right. We'll be okay. Okay. So what's the period here? It's going to be 2 pi over k. Now, let me stop for a minute. Are you guys with me? We're taking care of one problem at a time. I know We already know. There's an example in the book about just a normal circle, radius 1, center 0, 0. That's what you would say. And we checked, and sure enough, it's counterclockwise. Check. So far, this has got counterclockwise. Does it have the center? No. We'll worry about that in a minute. Does it have the right amount of time? No. Shit. Let's take care of that. What do we want our period to be for this problem? What does our period need to be? 3. I love it. It's 2 pi at the moment, right? So what do I need k to be so that this becomes 3? Can you solve that for k? What's more important than this specific problem is to remember what goes into this. So of course, the minute we're bringing trig back, we can bring everything about trig back. Oh shit. What's k got to be in order to make that true? 2 pi over 3 to solve for k, right? So if I make this 2 pi, let me write this in a different color. If I change these to be 2 pi t over 3. When t is 0, it's here, correct? Same as before. But now when t is 3, where is it? It gets back there, doesn't it? When t is 1.5, if t is 1.5, what's the angle I'm talking about? If t is 1.5, what's the angle I'm talking about? If t is 1.5. 1.5 times 2 is? 3. 3 divided by 3 is 1. So I'm talking about pi, correct? Then why did I pick 1.5? Because if it takes 3 to get around the whole thing, 1.5, it should end up there, correct? I'm just checking when I'm done. So sure enough, I put t equal 1.5 and I get pi. Isn't that freaking here? All right. So if you need it, if you have trig functions and you need it to complete something in a certain amount of time, that's what it's related to, the period. I know some of you guys might be like, I thought that was behind me. Every freaking thing can come back. Every mathematical concept you've ever seen in your whole life. All right, Jeff, don't be causing anxiety more than normal. Okay, sorry. But that's how you control the amount of time it takes for it to get through a cycle. It's through the period. Right? Now, I'm going to leave some part to you guys. I'll let you play around with things to figure out how to make the center correct. And there should be examples in there where there's a different center. I can't remember now. Bum, bum. Yeah, there is. There's a total beautiful example. Yeah, it basically gives you the answer. Yeah.
Can we shift like the center and then say like cosine 2 pi t over 3 and then shifts like 1 unit?
2 pi, sorry?
So
Shift?
cosine and
Yeah.
then that period and then shift that like 1 unit, just plus 1, because plus 1 has to be x.
Yeah, exactly. I mean, so normally you would want cosine to go from -1 to 1, correct? If the center is now 1, 3, you want cosine, you want the x part to go from 0 to 2, yes? Does that make sense? The radius is 1, and the center is at 1, 3. You want this to go from 0, you want x to go from 0 to 2. And that would just be, yeah, all right, that's, all right. I left about 15% of the problem to do for you, so. And again, I'll tell you, it's example 4 if you want to see the idea. But dude, I really want you to get that. A normal circle, doesn't it go from -1 to 1, -1 to 1, correct? And now you can see this direction is cosine. And the cosine goes from -1 to 1, correct? And the y piece is sine, -1 to 1. So what would I do if I wanted to just make it twice as big? I wouldn't make it x equal cosine t, I would make it x equal, how do I increase the amplitude of cosine? So it'd be x equals 2 cosine t, and y equals 2 cosine t. What do you think I would get if I did x equals 2 cosine t and y equals 1 sine t? What would the shape be? Yes, an ellipse goes out a different length that way versus that way, correct? Or vice versa, somehow squished or squished. You guys with me a little bit? And again, this is an aspect about just playing around with shit, right? Okay. Maybe. Yes. Section 10.1.
The last one,
51. Oh, okay. Ooh, yeah. Oh, this is awesome. I'm sorry. A and B are fixed now. Okay, so I'll give you a little bit of a hint here. Is everybody with me on what we've done? If you've been paying attention, I basically gave you the answer, which is a fault of mine. You should be upset when I do that, because this is your chance to play around with shit, right? I'm not going to give you any part of the answer on the test. Okay. So 51, they give you this. Look at that, that's neat. Okay, so we got A, we got B, we got O, we got point P, which is created by, this is a little weird, let me put B over here. Oh wait, where's P? P is, yeah, okay. So you see, if you move around the circle, won't that point be at a different location? So basically, if I picked another, let's see, where would it be if I went here? Then it would be, I go out, and it's the corner of that. Let me make sure I got the right part of it. Yes. It's the corner of this triangle that I make. So the trajectory that point goes on is the question. I'm guessing. I haven't read it yet. Oh, yeah. Blah, 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 blah. So, is everybody with me? So they gave us the big circle radius A, the little circle radius B. This is the angle to some general line I've put here. And then wherever you put this angle, it creates this little right triangle. Is that cool? So if I put it in a different place, let's put it, I don't have much left here, down here. So that means right here is where it hits this. Don't use the same color, John. Let's make it different. What do I got? I got green. So then I can make this right triangle here, and so the point would be there. It's kind of crazy. So it's asking us what trajectory does this thing take on? Let me see if I can squeeze one more in here. Oh, I've already got blue. Here. Beautiful brown, okay. All right, so then it would be this extremely thing. So when theta equals 0, it looks to be on the edge of the circle, but then it kind of comes in. And in the extreme, if I had theta equal pi over 2, do you see how it would be there? Because I can't make any triangle coming off of there. I'm not sure if you guys get the idea. So if I draw any radius, I drop straight down and I meet straight over from the outer circle, and the corner is where the next point is. So I'm going to do that infinitely many times as I go around the circle. So trying to figure out what is the equation for the trajectory of that point. Right. And right now you're all like, how the shit would I know? Anybody feel that way? You're all good? Okay, great. We'll move on. No? Okay. So if I take this first one, can you figure out, for example, what is this length, of course? Yeah, the big ass one, the A, correct? So that's, let me do this. I'm going to take this piece, put it there. Is that cool? So that's the identified P there. This is theta. Okay. And, so this is A. And this is how much? What's this? B. So what's this? A minus B. I like it. What is, let me see, how do I say this? You have this big ass, let me do a couple things for you. This is really just a playing around with shit problem. If you drop this down, don't I get a triangle here? So what I'm trying to do, let me just tell you what you're trying to do. If you could figure out general coordinates for that point. So I've drawn it several places. I don't care which one you pick. If you can figure out the general coordinates of that point, you're done. That's the equation. For example, if I knew the general coordinates for something were x squared plus 1, then that is the equation y equals x squared plus 1. Yes? Right? Okay. So what you're going to get is something more like this. R cosine t, comma, sine 5t minus r. Or maybe a and b. A and b are going to be in there, blah, blah, blah. So what's this? This would be x equals function of t. This would be y equals function of t. So what you're trying to do is just get coordinates for this point, assuming theta is any damn thing. So here's the x coordinate, yes? If I knew that length, wouldn't that be the x coordinate of that point? If I knew that length, wouldn't that be the x coordinate of the point? What's the y coordinate of the point? This length. Right here, this one right here, that would be the y coordinate of the point, yes? That length. I think I'm going to stop there. Do you understand? That is your goal. When you first see this problem, I completely understand if you're like, I have no idea. You want me to guess, right? But if you can write, tell me where that point is, just in terms of theta. So it's not going to be t's, it's going to be thetas. Theta is like our parameter now. Then you've given me the whole thing, because as I change theta, those will change also. So it doesn't matter where you draw, where you pick the general thing. I could put it there and I could do all the work. It's going to come out the exact same way.
Yeah, I was gonna ask you, do you have to do like trig? Like theta equals.
Oh yeah, you gotta do some trick. Oh yeah. There's gonna be some trick involved, definitely. Because as you're changing theta, trig is what kind of works with that the best, right? Yeah, and actually this is all about sides of triangles, correct? Sides of right triangles. That's trig all day, right? Okay. So, I mean, this x piece here would be this piece plus that piece, for example. That's one way to look at it, right? So you're breaking it down into, I need to figure out that length, and this length here, and I need to figure out this length here, based on theta and a and b. If I can figure out those two lengths based on a, b, and theta, I'm done. You'll have something like this. And by the way, this is for sure not the freaking answer. It's just shit I made up. Okay, maybe. And again, it's the last problem in the section. You know those are going to be a little bit more out there. Don't just not do it. Try something. If you can't quite get there, okay, the important thing is you try something and you just see where it goes. You got to just play with shit, right? I don't want every problem to be exactly this, next, exactly this, right? And I hope you guys don't want that either. Okay, that's enough. I'm sorry. Anything else that I can half-ass for you? I got to leave you guys something to do. Is that enough to kind of for you guys to go on? I mean, again, as a student, it's very often that problem, I'm sure, it's difficult to interpret how to even approach the answer. But if you can find the coordinates of that point based on theta, what does that mean? If you find the coordinates of the point based on theta, a, and b, that means it could be anywhere. You're done then. You found the actual trajectory if you do that, because it's going to be based on theta and a and b. So if I change theta, I change where I am, I can see where it's going. That's why that's the answer. So then you figure out, okay, how do I figure out the coordinates of that point? Based on what I know. It's a bunch of trig. This could have been a trig problem, easy. We didn't even need to make this parametric. This could have been a total problem in 170 or 176. This is a trig problem. Some of you guys are like, that's the worst phrase for me. Okay. Anything else from homework questions? Any homework questions? Does everybody have the 10-1 handout that I guess we didn't quite finish this, is that true? 10-1 handout? Everybody's got that? Oh, do you have your... Yes, okay. Oh. Anybody not get their test back, too? I have a feeling there's a few people, maybe. All right, everybody else has got the 10-1? You need it?
Go over 24 from the
Oh.
homework.
I'll leave with it late. All right, I got you. 24 from 10-1? Okay, so they give you, oh, it's not up here anymore, but do you remember what we just did? We tried to force the revolution to take 3 seconds.
Yeah.
How did we do that? We solved for what K had to be.
Yeah, so
What is K? They give you K in this one.
yes, pi over 4, right?
Yep. So how do you get the period? It's 2 pi over K.
So I did the period, but I don't think I got the direction right. So I separated like the sine and cosine.
Okay. And it says how long does it take? Is the motion clockwise or counterclockwise? Oh, okay. All you got to do is you put in okay, so it takes, the period is 8. Is the period 8, right?
The period is 8 seconds, yeah.
8 seconds.
Yeah.
So put in 0, and then put in 2, which is a quarter of 8. So if you do that, if it's going counterclockwise, you'll be somewhere and you'll be that direction from it, yes? So you just have to see. If t equals 0 and then I put in something later, I want to see which direction did I go from there. So if you put in a fourth of the wavelength of the period, you'll be able to tell if it's counterclockwise or clockwise. I think that's right from your perspective.
So what I did is I looked at the orientation of the calculator and see.
Oh, don't do that shit. All right. So, what was it? Sorry.
And I stated as t increases.
Where was it again? Oh, there it is. 3 sine 5 4 t, and y was what now? Same thing, but with cosine. 3 cosine 5. Okay. Is everybody cool? That's k. So the period would be 2 pi over 4, which is 8 seconds. Yes. So if I put 0 and I put 8, I should get the same exact output. That's not very explanatory. That doesn't tell me which way I went, right? Does that make sense? So what I'm going to do is I'm going to put in 0 and then 2. Because that's a fourth of the way through. So then I can see what direction I'm going. So what do I get when I put a 0 in? What's x? When I put a 0 in? What's the sign of 0? 0, yes? What's y? What's this cosine of 0? 1, so I get 3. So it starts there. Is everybody cool? That's t equals 0. That's where it is at the 0th second before it's moved. Do you guys follow? So this is where the particle starts, and then it starts to move. And all the physicists sit back and watch it. Oh, look at that shit. All right. They turn on the magnetic field, it starts to move around. They're like, oh, neat. So what about t equal 2 seconds? What happens? With t equals 2, this is sine of pi over 2, which is 1, so I get 3, yes? And 3, and now if I put 2 in here, I get cosine pi over 2, which is 0. So where am I now? I'm at 3, 0, yes? Which way did I go? Clockwise or counterclockwise? Clockwise. That's it. That's all you got to do. Does it make sense? Just start at the beginning time and then let some time pass. Not too much, because then you're back at the beginning. If you're doing circular motion, that doesn't help you. So it's really good to know the period, because then you can just say, okay, less than 8. Then I can see which direction I'm moving. Now, if you put it in and you're here, you don't know which way you went to get there. So you want to do like a fourth of the period. Does that make sense? Does that make sense? A fourth of the period. It should be a fourth. So I'm either going to be here or I'm going to be there. And then I know if I'm clockwise or if I'm counterclockwise. Yeah?
Is this the only way to like determine the direction, or is there like another?
No, it's not the only way. But it's a really good way to do it in the first place, because I'm trying to connect the graph of things to the functions. So if I kind of show you this, you'll be more inclined to do it, and you'll get more familiar with the graphs of these things. What really sucks about this, it's relatively simple, but you guys are not used to parametric, right? If I ask you to graph y equals square root of x, you better be able to freaking do that quick as shit, right? If I ask you to graph this, it's going to take a little while, not because of anything, it's just we don't do this shit all the time. So I want to try to, there are other ways to do it, but I want to try to get you to connect the graphing with the problem. So you start to get an intuitive sense a little bit. We don't have enough time for that really, but I try to do it again. Okay, anything else before we get back into where we left off? I think somebody told me, we didn't quite finish this. Let's see. All right, you'll work. We did do some of this thing, right? Let me show you what I'm talking about. On document camera, let's see what happens. Oh boy. Let's see what happens. Are you even? Well, that didn't do anything. Oh crap.
Flashbang.
Huh?
Flashbang.
Yeah, it was very effective. Flashbang was effective. All right. This guy, right? I'm pretty sure we did this one. I'm not sure where my copy went to that I had all the work. Oh shit, I gotta get used to this weird thing. Okay. We didn't do any of this one yet, is that true? Huh? We didn't do this one, okay, go ahead and do this one. If you weren't here, your input is T, and then you get an output, so you're creating points, and you can think about T as time. If you're worried about negative time, if you ever watch a rocket launch, what do you think T minus 7 seconds means? That is truly negative 7 seconds. It hasn't taken off yet, correct? So negative time doesn't mean you're actually going back in time. It just means 1 second before something happens. So negative 1 is perfectly fine. I might have done this up on the board maybe this way. Makes sense. I don't like doing this over here. I showed you guys how to do this. Did I? Yeah, I showed you guys how to do this in calculator, where you can do parametric and you can set it to ask. It'll just make these points for you. So this should be negative 4, is that true? This will be negative 5. 0 is nice. 1 is nice. 2 is nice. What is that? 8 minus 12, is that right? 4, and then 1. And then 3, 27 minus 27, that's 0. And then, what am I doing? 3? Okay. Right? This is relatively nice. It's just a different way to construct points. We have this third behind the scenes dude that's controlling both the x and the y. So there are my points. Does this show up on the graph? No. It does control when I am where, and it does kind of lead to the path I take. So when you graph parametric curves, it's not a complete graph unless you show me arrows saying what direction you're going. Right? And then you just got to plot points. -4, -5, negative just, 0, -3. Got to keep track of where you're going when. -2, -1. So I'm kind of going this way. -4, 1, and 0, 3. So it kind of look like this. Feel pretty good about that because it's a cubic and a line. So the y direction is a straight line. So the y points are going, do you see how they're all 2, 2, 2, 2 apart in the y direction? So y is growing linearly, slope 2, right? X is going, this is interesting. Can anyone tell me, well, let's see. This is a little bit freakier, but t cubed minus 3t squared, I'm not going to analyze that. You could do a bunch of math 180 to it and figure out the maximum min and the curvature concavity and the inflection point, all that kind of bullshit. But do you see how the y looks like a cubic? I mean, not the y, but the x. The x looks like a cubic as the y kind of moves up slowly, linearly. Yes, maybe? So you can kind of imagine, if I kept going, this should keep going this way, and that should keep going that way. Right? Okay. I like it. But I don't. I stop at -1 and 3, so you make sure that those are ending points. Not too bad, right? What about this? How am I going to do this? Oh, shit. Everybody's at home. Maybe you should see this. Interesting. Anybody? How do I get rid of t? That's the parameter's t. So which one am I going to solve for t? Hell yeah, I don't know how to solve x for t. Are you kidding me? Right? So if I take this and solve it, I'm going to add 3 divided by 2. So I get t equals y plus 3 divided by 2, yes? And then I can shove that stuff in to x. So x equals y plus 3 over 2 cubed minus 3 times y plus 3 over 2 squared. There is absolutely no need to multiply that stuff out. Okay? Let's see if I can do this real quick. What did I say? No. All right. Desmos. There. Third power minus, this is exciting, minus 3 times y plus 3 over 2 to the second power. So watch this. What I just put into Desmos, oh, that's not going to work yet. We're going to do this too. Now, of course, this is going further than we wanted it to, but if you just look at the middle part, isn't that what we just did? So I put in the rectangular coordinates, right? The rectangular equation. So let me build the parametrization of this. T cubed minus 3t squared, is that right? Oh, I can't do it that way. I gotta remember how to do this. Okay, so to do parametric equations, you make one point. The x piece will be the x definition, t cubed minus 3t squared, comma, 2t minus 3.
I think you have to square the
Oh, that's awesome. That's because, let me pull it over here. I love this so much. Okay, there we go. Oh, I I see what I did. Okay, there. Why are you doing that? There you go. No. There you go. That's good. Hey, this is squared, 2t minus 3. Everybody's hanging on. It's freaking out. Okay. No. Hold on. There it is. Huh. Oh. Okay. What was it? Negative 1 to 3?
Yeah, yes.
Something like a little freaky. Let me think about what that is. This is interesting. Equals. That was 3 over 2. We shoved it in there. Yeah, let me show you what I got. Let me just be open with you. This is not quite, it's shifted.
You deleted the square root of the second one.
Oh, I did, thank you. Alright, there we go, that's what it should be. So now they're perfectly lining up with each other. So if I turn this one off, I get that. That's kind of cool. Would have been much more impressive, Jeff, if you would have noticed. There we go, sorry. So it's really nice in Desmos when you just do parametric, you can control what t is, so you get the part. And of course, if you just graph the rectangular equation, you can get the extension of it. Right? Okay, that's it. All right, so then what about, whoever's got their graphing calculator. Have I shown you how to do this in your graphing calculator yet? I did? Good. Madison, still want to get hardest count for some reason. Sorry, everybody else gets that. So if I want to put this in, I go to mode, and I change to parametric. And then I got that set up. And now I can put in there x equals 2. So go ahead and do this. I'm going to sort of put it in, but I'm going to let you guys put it in and hit enter and see what happens. Has anybody got a graph? Yeah, so if I zoom out, let's see if I just make the window out a little bit more. Oh, lines are crazy. I see. Zoom sense. So what's that? That's an elliptical. What's interesting about it?
Diagonal.
Yes, it's been rotated, right? So in rectangular coordinates, can you start to understand If I have y equals x squared, that's a parabola straight up and down. If I have x equal y squared, that's a parabola like this. Some of you guys at some point, I don't know if you thought, well, how the shit do you get a parabola that is like at a diagonal? Rectangular coordinates sucks big time for that shit. But polar, it's not that hard. So what, real quick, what is going to happen if I get rid of this 3 cosine 2t right here? Let's try. That is a normal ellipse, correct? Okay, so it seems as if I add something, I forgot what it was. Oh yeah, it's right there. 3 cosine 2t. That will make it go at a diagonal. So let's, if we play around this a little bit, what if I made this plus 6 cosine 2t? Makes it skinnier and longer. And I like it. What if I made this cosine 3t? Now we're talking, right? This is like logo design. No? Okay, I like it. Okay, but anyway, again, I really hope some of you guys just start. I mean, it's insane the number of things you can get out of this. And like I said, if any of you guys know the spirograph game with the gears, it's kind of neat. You can actually figure out the equations of these things. The funkiest pictures are the ones that have differing angles. So if I make this 5t and I got 3t and I got 2t, that's where I start to get some truly nifty stuff. This is like, I'm going to call this the atomic bell. What do you think? Isn't it like a bell here? Or like this looks even more like a bishop. Anybody plays chess?
Yeah, let's see a pawn.
Huh? A pawn? Even better. So it looks like a pawn. So the atomic pawn. I love it. I kind of wanted it to be atomic bishop, but it sounds more badass. It's like a D&D character.
It will always be symmetrical.
No. I'm using, let me see. What's the quickest way to make that happen? Well, the quickest way to make that happen is use something other than sine and cosine. Sine and cosine are inherently symmetric, right? They have all kinds of symmetries. But if I just introduce, let's see what happens if I do minus t. Well, this is going to be really funky. Yeah. That's a little less pleasing, yes? Okay, looks like something drops spaghetti. We went from atomic bishop to drop spaghetti. Poor little thing. Anyway, okay. So it's just interesting. We're not going to get to talk about how to revolve shapes. That would be more in a little bit in Calc 3, but not really a lot in Calc 3 to be honest, which is unfortunate. Yeah.
So for when you turn it into a Cartesian equation,
Yes.
you always have to put it in terms of y.
No. The one we just did was oh, I see. In terms of y, I see. So, no, it could be either way. It doesn't really matter. In fact, sometimes you can get something you can't even solve for x or y. Yeah. Huh? You just don't. You can't. So guess what you do? In general, if you can't, you don't. You can try, but then Yoda's going to get angry at us.
We're just gonna try.
So let's see. Okay, that's enough of that. That's enough playing. So now we're basically done with 10.1. 10.1 really was just the basics of graphing, parametric stuff. Now we're going to get into some calculus with parametric stuff. This looks like a Hubble deep space telescope picture or something. Or it looks like the TV and Poltergeist. They're here. All right. What are the back in Calc 1? If I give you a function, it's going to be a really silly question, okay? Some really crazy basic shit. What's one way to denote the derivative? Nothing major. Just what would you do if I said take the derivative? What would you put? Y prime is f prime, yes? So what's another way to write y prime? What's the more dy dx. And that, of course, is the better way to do it if you talk about units. The beautiful thing about writing ratios of infinitesimals is the units are right there for us, right? And of course, if any of you guys go much further in mathematics, this becomes much more important because I'll have, if you go to Calc 3, you'll have multivariable functions, and you might want to take the derivative only with respect to z, not with respect to w, or x, or b, or a, right? So you're going to want to write dy dA, or dy dz, or dy d whatever. Okay. Right now, think I'm going to go. Okay. So watch this. If I have something defined in terms of t, parametric equations, right? I want to figure out, and again, why does this make sense? I should have kept this up here longer, but if you look at your calculators, if you're playing along with me, you got the spaghetti on there. I don't know what you got on there. Pick a point. Can't you see a slope? In fact, let me do this. This will still work, Jeff. Sorry. Yeah, if you're there, you just have to be turned on. You have to wait for Sony to do its advertisement. Come on, Sony. Oh yeah, I've got to turn the damn thing on. I got to turn that on and turn this on. You're blinded. Tricked me. Okay, so if I put this in the right place, this is going to be. Oh shit, man. How do I zoom? So like right here, isn't there a slope there? Any point on this, I've got, what would be true about the slope there? That slope would be infinite, right? You with me? Okay, so for any parametric curve, it's not a function. Is this a function? The weird thing is, this is not technically a function of two variables because it doesn't pass the vertical line test, right? But is this a function of t? Are the points themselves, are the x and y coordinates functions of t? Yes. Right? So there should be a way to get the derivative relatively easily because both variables are functions of some third variable that controls them both. I should be able to get the derivative relatively easily. Thank you. Okay. There, look, that's neat. And of course, none of you saw that, so, oh well. Oh shit, it's probably a little too cold now, because I just went crazy on the, sorry about that. It was stupid hot in here earlier. Okay. So watch it, this is too good to believe. So in this case, dy dt, get out of there, Jeff, you're getting ahead of yourself. If I just multiply, or if you can think of it as division, but of course there is no division, it's all multiplication, just multiply by reciprocals. I can just divide the top and bottom by the same thing. And in fact, in this case, what I want to divide by, what can I take the derivative of x with respect to? What would make sense? It's a function of what? T. So don't I want to take the derivative of x with respect to t? As long as I do the same thing to the top? So believe it or not, that's it. That's how you get the derivative. So for example, let's do, let me see, is that a relatively simple one? Yeah, that is a relatively simple one. The one we just did, here we go. X equals t cubed plus 3t minus 3t squared. Y equals 2t minus 3. What is the derivative at t equal to 1? Let's do that first. This is part A. So it's literally just what's dx dt, what's dy dt, and then take the ratio dy to dx. So what is dx dt?
3t squared and minus 60.
What's dy dt? 2. Right? Don't blame me for being a little suspicious. Can't be that easy. So dy dt divided by dx dt is 2 over 3t squared minus 6t. So what is the derivative of the function of the parametric equations at t equal 1? So again, 2 over negative 3, right? So negative 2/3. Is that cool? Yeah? Okay, so let's see how it works. Let me redefine this. Where'd it go? T cubed minus 3t squared. And then, why are you not, well, I don't know. 2t minus 3. And it was from negative 1 to 3, is that right? That we did it? Doesn't really matter. Okay. So let me see. This is fine, John. This is fine. This will work. That. It wants me to stand in front of it so it can blind me. No, I don't know what it wants. Okay. Okay, so it's kind of cool. What point are we talking about here, by the way? Does anyone think I haven't told you what point this is about? Because I have. Which point are we at on this graph? What's the only thing we know? Only thing we know. T equals 1. All right, so what's x? Oh, this is funky. Negative 2, right? And what's y? Negative 1. So I'm looking at negative 2, negative 1. So at negative 2, negative 1, is the slope negative? Yes, I love it. We can't tell it's negative 2/3. We're not that perfect. But it does look a little bit less steep than negative 1 would be. Right? Okay, I love it. I do, I really love it. So if I try to do, let's try to do this point. So let me ask you guys, what would t have to be to get here? And you can look back at the work we did earlier because we already did that. But you can kind of look at x. X would have to be 0 and y would have to be negative 3. So that's t equal 0. So if t equals 0, what is the derivative? 2 over 3 times 0 squared minus 6 times 0. Undefined, infinite. And sure enough, the slope here becomes infinite. Right there, becomes infinite, just for a moment. And then it keeps going around. You guys follow?
Yeah.
Thank God. I mean, if I would have just said, how do you think we do derivatives for this stuff? It would have been like, holy shit. It's only this. This is insane. This is so beautiful. Let it be beautiful. Okay. All right. Blah, 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 blah. Let me see, is there anything else weird? Oh, here's a little bit weirdness. Here's a little bit of weirdness. Okay, let me turn this off. This is that's weird too. Here's a little weirdness. That's the first derivative, correct? What if I want second derivative? What if I want to know about concavity of these things? So I'm going to erase this. Let me see. So dy dx equals dy over dt over dx over dt. Right? So now I want to know the derivative. I want to know this. So if I call this, let's call this u for a minute, right? I want to know what du dx is. Yes? You with me? Just to make this look a little better. Are you with me? Okay. If I know the first derivative, the second derivative is just the derivative of that, correct? There's a lot of shit going on here. Let me just call it U. Why am I allowed to do that? Because I don't know what that is. So I'll call it whatever the hell I want to. Nah. All right. Then I do what we did before. du dt over dx dt, yes? What's U? Isn't U dy dx? Right? So that's how you find the second derivative of this. And then you would do a similar thing if you want to find the third derivative. Are you guys semi with me? No? Is that good? Is that bad? Are you guys okay? Are you guys concerned about what you're going to have to do? I don't know what's happening up there. So again, so the one we just did was, I should have left this up here, but I can't plan ahead. T cubed minus 3t squared, 2t minus 3, and we got dy dx was 2 over 6t squared minus, no, 3t squared minus 6t, right? Yes? Okay, so what do I need to do to figure out the second derivative? So I can figure out some concavity going on. Concavity. So that'll be d by dt of this over dx dt, which was this stuff again. Doesn't it look exciting? Okay. This actually bores me. I don't want to. I mean, that's just, right? What's important is what to do. Derivatives, you should be able to just eat those up. Yeah, if you wanted to do quotient rule here, you could pull this up and do just the normal derivative, whatever you want to do. But that's the process to get the second derivative. Okay. Not immediately intuitive, but we just applied the idea, and that's where we ended up. Bam. Okay, maybe. Okay. Blah, 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 blah. Okay. Yeah, there's not much more to it. So let's do, oh, that's right, I only brought this. That's okay. So where things are going to get a little bit weirder, you could probably imagine this, is, so that's derivatives. Does everybody agree that's relatively easy? Yes? Derivatives are almost universally going to be easy, no matter what coordinate system you're in. How many coordinate systems do you guys know about? You got the x, y, even z, right? So the rectangular coordinate system. Do you guys know any more? You guys should know, spherical, which is polar, well, cylindrical is polar translated to 3 dimensions. Spherical is truly spherical. It's got a radius and 2 angles, believe it or not, right? I can sit down and try to write out about 8 coordinate systems, and then there's multiple adjustments to each one. So why, do you guys understand what I'm saying right now? So parametric is sort of like just a generalization. You can build stuff based on t. It's not really a general coordinate system like the rectangular one. We call it rectangular because I create rectangles very easily in it. Polar has to do with circles. That's why you have the north and south pole. So of course it's all about drawing circles. If it's circular, it's going to be able to draw that work like crazy. Every coordinate system has certain problems that work easier in it. So obviously, if I have a cylindrical coordinate system and I have a problem that has cylinders, I'm like, okay, I want to use that. If I have a problem that involves enclosing charges in some kind of spherical conductor, right? I'm going to use spherical coordinate system because it's going to just eat those equations up. But those equations look really gross in our basic rectangular coordinate system. Okay. Not really sure why I went on this tangent right now, but we are going to start to get into polar. If any of you are taking Calc 3, anybody taking Calc 3, you're going to get into spherical, you're going to get into cylindrical, right? If I ever teach it again, I like to give a little bit of a hint about some other ones that are sort of like not part of the class, but those are the two you're going to have to definitely be working with. Okay. Why did I go that way? I don't know. So what we're about to get into is how to do the next level. So derivatives, relatively easy. What's then, of course, naturally the next calculus thing we want to do? Integration. I love it. So now I want to be able to integrate. So let's go back to Calc 1. I give you a function, and I ask you to find the area under the function from x equals a to x equals b. All right, set that up real quick. Set up the thing that would answer that question. You obviously can't do anything with it, but set it up. All right, should be done. What do we got? A to B. F of x. Let's put y in there just to be different. It doesn't matter. F of x is fine. I'm going to put y in there. Dx, right? You with me? F of x, y, doesn't matter. They're both the same name. Now, instead of something that's controlled by x and therefore x would rule everything, right? We're going to have something where both visual coordinates are built on t. So I'm going to need t to control everything. So this is what x is doing. X is going from a to b. So if we transition to, let's say I now have x equals a function of t, y equals a function of t. Can anyone tell me? So I got y is this, correct? So let me put in here, y is g of t. Let me say that t is going to go from alpha to beta, because it doesn't have to be equal to this. I want that to make sense. What's alpha? It's the t that makes x a. What's beta? It's the t that makes x b. You with me? Does that make sense? So if I make t 1, it might make x 7. So if a is 7, I want this to be 1. You guys something with me? So obviously the parameter t doesn't have to have the same values of x. It just has to be whatever it has to be to make x do those things. Okay, maybe. That's why this is a, and that's alpha. That's why this is b, and that's beta. Okay, maybe. So this will be from alpha to beta. Y is g of t. What's dx? You can do it. If you made the substitution, x equals sine beta, what's dx? Cosine theta? Overthinking it, d theta. Right? So if I had x equals natural log of t, what would dx be? 1 over t? dt. So x equals f of t. So what's dx? F prime of t? dt. This is exactly this. When t is alpha, x is a. When t is beta, x is b. So this leads to this. Do you guys see how those are basically the same exact integral? Maybe? No? You're all like, I'll humor you. Some of you guys are just flat out, screw that, I don't know what the hell you're talking about. Everybody's cool with this. This is the whole point of parametric. That leads to this, and then this is 180 shit. And then, of course, we just replace what we're currently working with in place of what we got here. The idea doesn't change. It does not fundamentally change. But now, I'm traveling along the t direction. Now, what's weird about t is it doesn't have an axis that shows up. There's no t-axis in our visual, yes? But as I travel along the thing, I am traveling along the t-axis in a sense. So a little bit weird. Okay, so this here would be very difficult to actually visualize. I couldn't do Riemann sums very easily here. So let's do an example. Okay, so let's see. What if I have, so that's the process. Given these, I calculate this, and I construct the interval, and then I just do it. So let's take a problem right out of the homework. Let's see. Shit. If I could see anything. Oh, sure. Okay, let's try that. Woo-hoo. Okay, so I got x equals sine squared t, y equals cosine t. And they tell me, they give me a visual. Okay, so I want this part of it. So what seems to be controlling everything is this to this, yes? You guys understand, the way they gave me this problem, they didn't tell me what alpha and beta are, correct? I know what x and y are. I can totally, we'll worry about alpha and beta in a second. Can we just set this up? What this would be would have to figure out to build the interval. What's the only thing I'm missing besides alpha, beta? What am I missing for the inside? This is just g of t, correct? What's g of t? So cosine t. How do I get this next bit? But what I have to do? X prime. So what's the dx?
2 sine t cosine t dt.
I'll love it. So this will be, you need more room. 2 sine t cosine t dt. All right, let me stop for a minute. You guys see how to build that? And if you want to, actually, you can just kind of think of this as, let's say y times x prime. Does that make more sense? Whatever makes sense. Okay, so this is, x is the f of t, y is the g of t. That's the important thing to remember. Okay. All right, so now if we could just figure out alpha and beta, this is a very exciting trig integral. Yay! So how the hell am I going to figure out alpha and beta? Well, what does t have to be on the y-axis? In fact, what does it mean to be on the y-axis? What do I know something about? X equals 0. So for these two, I know that x is 0, right? For this one, I know that y equals 0. Okay. So when x is 0, what's t? In fact, what does x equals 0 mean? It means that sine squared of t is 0. I like it. So sine squared of t is 0. So t is either 0 or pi. I love it. I'm kind of assuming we're sticking between 0 and 2 pi. They don't say it, but it's a very small part of something. Yeah, so it's got to be between 0 and 2 pi. You guys with me? So now, real quick. If t is 0, what's y? 1. So this looks to be t equals 0. Is this cool? If t is 0, is everybody with me? If t is 0, x is 0. If t is 0, y is 1. So that looks to be when t is 0 right there, right? What about when t is pi? What's y? So that looks to be t equal pi.
Can you change the color?
Certainly, yes. You make it, do this again. But please tell me, I'm trying to, is that better?
Yeah.
Beautiful, beautiful brown, okay. What was this again? Can't remember what my point was here, shoot. Sine squared equals 0, yes. So when x equals 0, is everybody, I'm trying to figure out what those are. Again, I'm trying to figure out my alpha, beta. Wouldn't it make sense that one of these is alpha, the other one's beta? It all depends on how I'm moving to get through this across this region. So that's equal to t equals 0 and t equal to pi. So this leads to 0, 1, and this leads to 0, negative 1. So this was t equal to 0, and this was t equal to pi. So I bet you anything this will be t equal to halfway between. So that's 0, that's pi. So what do you think? Pi over 2, let's check. If t is pi over 2, what's the sine of pi over 2? Squared is 1, so that looks to be, and what's cosine of pi over 2? Okay. So that's going to be 1, 0. That looks to be there. So can anyone tell me what these are? Where does it start? For what value of t? T is 0, correct?
Yeah.
Up to pi. That gets me through this whole region, yes? I like it. I like it. I don't know if you guys really understand. Now, this is a little bit different. Some of the problems are just going to tell you what alpha and beta are. They're just going to tell you t between this and this, and you're going to go, thank you, problem. You're going to just do it. Some of them are just going to say, figure it out. Good luck. You just have to reason it out, right? And now the question is, can you guys remember how to integrate this? And you're like, oh, good. Chapter 7 is coming back. Thank you, Jeff. Who remembers how to do this? Some of you guys are making a face like that. I love it. I was told it'd be much. No. You can come back whenever wants to. How do I do this? Which trig piece is free? It has nothing else happening to it. No, it's got a square happening to it. Do you understand what I'm saying?
Yeah.
Sine is free. So I can put sine with dt. So if I got sine t dt, that's du, so what must u be? I don't care about constants. I really want this to make sense. If I put the sine with the dt, that looks like it's going to be a du. It wants to be a du. What's u got to be so I get a du of basically sine? Cosine. And then there's a negative, right? So I don't care about constants. Who gives a shit? I can always make those do what I want to. All right. So then I would let me write it again up here. 0 to pi 2 sine t cosine squared t dt. I would let u equal cosine. So du is negative sine. So put in negative. So give a negative. So this, and this make du. 2. And u is cosine. I'm going to put this in parentheses. Oh, Jeff, just go ahead and change them. You should do that. If t is 0, I get u as 1. If t is pi, I get u as negative 1. Is that cool? Okay. What's the integral of 2u squared? Cool. From 1 to negative 1. So when I put negative 1 in, I get negative 2/3 times negative is 2/3. Minus a negative, so plus 2/3 times 1 cubed, so 2/3. I get 4/3. Crazy sauce. By the way, I've kind of drawn, so what we just found is this area. Is this a half of a circle?
Yeah.
Look at the equations. Is this a half of a circle? No, because x is being assigned squared. You guys with me?
Yeah.
So this is not quite the real, I know I drew it like it was half a circle because that's what they have in the book, but it's not going to be half of a circle. It's got a different curvature because it's squared here. Otherwise, I would have said, what's the rate? If this was a circle, wouldn't the radius be 1? Right? And then a radius 1 circle has an area of what? Pi. Yes? But 4 divided by 3 is not equal to pi, correct? I don't know if you guys are with me or not. It's always good when you're integrating stuff, it's area. If the shape, the function I'm looking at is a basic geometric function, I can always check my work by just doing geometrical areas. Is this actually a circle though? No, because it's squared on the side. You with me? So somehow it's a little bit of an emaciated circle, so it got a smaller area than it would have otherwise. Well, and plus it's half of a circle, so if it was truly a circle, it would be, what would be, pi over 2? Pi over 2 is roughly 1.57. And 4/3 is 1.33, right? So it's not as far off as I thought, but it's just a little bit, maybe caved in a little bit. It's not covering as much area as a normal, so if that would have just been sine, it would have been just a regular circle. I guess all that stuff I just said was on the side, right? But it's stuff, as you work through stuff, you should be developing ways to kind of check your work. And anytime I have something roughly geometric, just knowing the area of this and that it should be sort of close, okay, those are close, okay, I feel okay about that. If you would have gotten 12, that's freaking wrong. You can kind of estimate what your answer should be. Okay, maybe. Okay. Okay, real quick, I just want to, I don't know why I keep wanting to say more about this. If I square something less than 1, between 0 and 1, what happens to the number? Gets smaller. I love it. So these sides actually are more in than they would be for an actual normal circle, which is why the area is smaller than it would be for a normal semicircle. Everything I just said is extra. You have to know what I just said. Okay. So you're all like, say what I need to know then, man. All right, I'm sorry. Where do I want to go next? Yeah, there's really not too much more to this. Let me see. Where's something weird? Blah, blah, blah. Blah, blah, blah. All right. Let's see. Well, that one looks a little bit weirder. It's all the same stuff, though. Let me see. Did they give me anything weird? Oh, that's a little weird. Yeah. Yeah. Look at this here. Okay. I'm gonna erase this here. So there's a problem that gives us these. X equal 1 minus t. Oh God, I gotta bring my freaking glasses. T squared, I believe. If anybody's got their book on 10-2, number 40, number 40. Pretty sure it's a squared. Don't get old, kids. Y equals crap a half. T minus t cubed, I think. I believe. And this is a little bit weirder. So if they graph it for us, and they get something really, really, really nifty. So they want to know this area here. Okay. This is the great blue calculus whale. Okay. So what all right. There's two ways to kind of do this. Let's do it the straight up way. So they're kind of telling me that's 0. Let's double check this. So what's weird is I need, so to enclose this whole thing, don't I need t to start at 0 and, not t, but I'm sorry. I need xy to be 0, 0, and then I need it to become 0, 0 again. Do you guys agree with me?
Yeah.
If I want to enclose this whole thing, I need to start here and I need to end there again. Yes? But I really want you, do you understand how this is not one point? Do you understand that? This is, I love it. You're all like, it happened. He's off his meds. What the shit? What's up with this guy? That is not one point because now we're involving time, another coordinate, time. Right? So I go down the road and I go through this point and then I keep going and then I come back to this point. And in Virginia, you can actually have a street that intersects another street. It was awesome. I can't remember the name of the street, but you live in the corner of Llewellyn and Llewellyn. Oh, that's weird. So that is 2 different points because it has 2 different t values, at least. Yes? So how do I figure that out? So I want the point 0, 0. So of course that means that I want x to be, and sure enough, aren't there 2 t values that make that happen? What are they? Plus or minus 1, right? In fact, let's be more specific. Positive 1, negative 1. What is y when t is 1? Zero. I love it. What is y and t is negative 1? 0. Okay, so good. So those two t's make both x and y 0. I like it. So really, in this case, let me think. It really doesn't matter because they don't tell me. No, they don't. Those doors. Well, we could figure it out. But I would go from -1 to 1. Let's see what happens if we do this. -1 to 1. And then what do I need to build this? So everything we just did was just to figure out our limits for our interval, correct? Did I just turn it off? Sure, I won. Okay. Does everybody understand? There's going to be two separate problems. First problem is, what are my limits? And we've had this before. First problem, what are my limits? Second problem, easier problem, because it's recipe-ish. What do I put here? Whatever y is. What do I put next to it? Derivative of x. What's the x? Yes. And then that is a thank God problem, yes? It's just a stupid little polynomial. Nothing, no offense, little math problem. This should be pretty simple. 2t to the 5th over 5 minus 2t cubed over 3 from -1 to 1. So I get 2/5 minus 2/3 minus -2/5 plus 2/3. Right? So some of you guys might realize there was a shortcut here, and of course there's symmetry here, yes? I could have gone from this to this, but that would involve figuring out a different t value, and then doubled it. Right? I could have went from, anyway, why do that? This is pretty straightforward. So 2/5 minus 2/3 is 6 minus 10, -4/15, plus -4/15 to get -8/15, which tells me I had those the other way around. Damn it. Let me see, why is that? Let me think. Why is that important? Bump, 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 bump. Bump, no. Yeah, one is going this way, and one is going this way. So let me think, is there a way I should go? Let me think. Can you guys see what the problem is? This should be positive, this volume, this area should be positive, and I'm getting a negative. Did I do all that right? Did I leave? No. Yeah, I did, darn it. So then, for some reason, it needs to be the other way around. I gotta think about why that is. Why would that be true? I don't know. I'll have to come back to that one. Yeah, that is 1. So, yeah, I was going to do the top half and double it. Basically, if you get the negative, it's just these are the wrong way around. I can't remember why, what part of the problem. All right, I'll have to think about that one. There's something about this that tells you which way there should be, I think. Well, let's do this. Let's not do that. Let's not waste time. I'll figure it out. All right. Is there a different type? No. Okay. Okay. All right. Blah, 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 blah. Okay, okay. So the area, like I said, it's got the two steps, figure out the bounds and then it's just figuring out the dx. I'm gonna have to look back and see, I gotta remember to look at this problem and remember what tells you which way these should be, because the answer should be positive, obviously, which means these were reversed. There's something really obvious that I'm just not seeing. But, okay, I'll look at it. The last part of section 10.2, which is what we're in, by the way. 10.2 is about the calculus of parametric curves. The last part deals with something I'm not sure everybody talked about in Calc 1, so I'm going to really quickly review the idea of arc length from Calc 1, and then we'll talk about how to do that with parametric equations. So arc length really just means, given some function f of x, I want to know, I don't want to know the area underneath it. I want to know how long this is from A to B. So just given some f of x, I want to know how long that segment is, which if you really think about it, sounds very hard to do. If it was a straight line, that's easy. If it's a straight line, I got the distance formula I could do. But the distance formula does not apply for all this curvy business, right? Do you guys ever, does anyone remember if they've ever, do you guys do arc length in Calc 1?
Yeah.
You did? Okay. So let me show you if you didn't. Here's a really cool way to look at this. So if I take a little piece of this, if I look at one little bit and I move a little bit over in the x direction, maybe I'll go a little bit more so everybody can see, and a little bit in the y direction. And then I get this. Now obviously, dx is infinitesimally short, dy is infinitesimally short, but it's already hard enough to see what I've done. So I'll just do it that small at the most. Can anyone tell me how long this segment here would be? Let me call it ds, but I want to know what that is in terms of dy and dx. Why is that an easy question? What shape did I just make? Triangle. ds equals, ds squared equals dx squared plus, holy shit. So then ds equals, we're assuming that arc length is positive, so I choose the positive root. Nothing crazy yet, that's right? That's nice. I could do that with my Math 90 students, even though they don't know what d is. It doesn't matter, it's just Pythagorean theorem. I say that, I don't have Math 90 students anymore. Now watch this. How do I get the complete length then? Don't I want to add up all of these isn't there a bunch of DS's running around? There's a DS, there's a DS, and you get a DS, and you get a DS. Are you guys with me? Isn't there a bunch of DS's as I move around? So don't I want to add them all up? From what to what? A to B. This looks wrong though. What's wrong with that integral? Some of you guys don't realize there's something wrong with that integral. That makes me sad. If I wrote this, what's the integral of 2x? Anyone know what that is? What's the integral of 2x? What's wrong with what I wrote though? Yeah, you gotta have, that's so freaking important. The symbol doesn't make sense. It's a bookmark, a bookend symbol. That's what integration is. It's a bookend symbol. Both of those go together. Without one, the whole thing doesn't make sense. You have to tell somebody what you're integrating in respect to. And of course in Calc 3 it's going to be even more important because you're going to have multiple variables. You got to know which one you're looking at. So let's do something weird. Can you please factor out a dx squared? In fact, let's just do it like this. Take a dx squared out. Like that, right? I'll do the first bit. 1. Okay. I did half. Beautiful. All right, like that, right? What is the square root of dx squared?
Yes.
Understanding that dx is a positive movement, right? So its square root is just dx. And now I got this. Now that looks like an appropriate integral. So given an f of x, all I have to do is take its derivative and plop it in there. Now, of course, if anybody did this in Calc 1, very quickly, if you make the function anything other than a select few functions, this is impossible to integrate. Maybe? You understand? Yeah. So, it's a little bit lost on us in Calc 1. But now, you guys, you got a whole shitload of more ways to integrate stuff. And you're like, oh shit, all right. So, this is old news, by the way. You all with me? That's old news. This is nothing new. This is just a review of Calc 1, and I'm sorry if your teacher never went over this stuff. This stuff they should have went over. But is it very difficult? It's pretty simple to understand. And actually, again, whatever they give you, you take its derivative, you throw it in there, and you do this integral. Done. Okay. So how do I do this in parametric form? Well, what I do, I'm going to start here. I'm going to write this again. We were here at one point. I think this will be the last thing we do. Ever. No, I mean tonight. It's very ominous. Oh, there it is. Okay. Blah, blah, blah. So, remember what we did earlier. X is f of t, y is g of t. So what I want to show up in there is stuff to do with t. Now, everything's driven by t, correct? So let me see if you guys are cool with this. If I have a 7 sitting here, just stay with me. I'm going to say something really weird. If I have a 7 sitting there, can't I divide by 2 and multiply by 2? Is it still 7? Right? Okay. So look what I'm going to do. I'm going to say dx squared over dt squared. Right? And let's just make it dx dt squared. So just divided by dt squared. Divide by dt. So I divided the whole inside by dt squared. So I'm going to multiply by the square root of dt squared on the outside. There. And now we integrate from alpha to beta. We usually use those alpha and beta for t. Funky shit. So let's do it. Let's try a concrete example maybe. Let's see if we have a really quick one. Yeah, that's a very quick one. Let's try that one. And then we'll head out. So what if they gave us x equal cosine t, y equal sine t? 0 to 2 pi for t, blah, blah, blah. What's it say? Blah, 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 blah. What's the problem? Let's see, blah, blah, blah. Oh, you killed me. Oh, okay, so, yeah, so what if I want to figure out the arc length from 0 to 2 pi? So let's try that. So what do I need to build that integral? I need dx dt, right? What's dx dt? Negative sine t. What's dy dt? Cosine t. I like it. What else do I need? Nothing. I just need to know alpha and beta, but they gave me those. 0 to 2 pi. Square root of negative sine t squared plus cosine t squared dt. What is sine squared t plus cosine squared t? 1. What's the integral at, huh?
Is this negative sine squared?
It is. So of course it's positive sine squared. Because the negative is squared, right? Okay. What's the integral of 1? dt. What's the integral of 1? t? From 0 to 2 pi, so you get 2 pi. Now why is that silly? Does anyone know what the circumference, that's basically what we're figuring out. The arc length of a circle of radius 1 is the circumference. What's the circumference? 2 pi r. R is 1. 2 pi, right? That's a little bit boring, but still, it's nice to start with 1 that you can actually verify just using geometric stuff. You guys see that? You guys? So now I can give you like the spaghetti one, right? And I want to know how long is this line here? Or you just do this work. Obviously, I have to be careful about what I give you because it's really, really quick for this to go bad. You got a big ass square root with nothing outside, right? So that could very quickly become something that we'd really rather not integrate. Yes, if I'm not careful. Okay. You all have very interesting looks in your faces. This is not terrible. If you did arc length before, that's awesome because this kind of builds off of that. If you didn't, I'm sorry. Otherwise, this is not that terrible. I wanted to get in polar, but we're gonna end now, I think. So next time we'll do polar coordinates. We're gonna do a little review of polar coordinates. I'm gonna give you some examples of my favorite polar graph paper. And then I'm going to tell you just to go print your own damn graph paper yourselves. But I'll give you a couple examples for next time in class. Okay? All right. So let me know if you have any questions. Otherwise, I will see you next time. By the way, the next test is a week from this Wednesday, correct? Yeah. All right.
Jeff, what's the name of that teacher, Professor Lyons?
Michael Lyons?
Lyons,
Yeah?
I just remember.
Okay.